Thank you. Well, hi everyone. Okay, so I will present this joint work with Pablo Aremon and Simona Ronchi de la Roca, which is there too. It is about a new proof of normalization for idempotent intersection types. And the first thing to say here is that it is not a new result. We know that programs terminate in this system, but it is a new way to prove that. And so the motivation is to find simpler ways of proving that property. So there are the usual way of proving this property is a semantic approach, which is the approach of reducibility candidates, where it was introduced by Tait and Girard. I'm sorry, French people, if I obviously mispronounce Girard. So the idea is to find the notational semantics for the types, which is based on termination, and then to prove soundness of the type system against that semantics. And there is another approach, which is a syntactic approach, which is to find a decreasing measure. And a decreasing measure is essentially to find something related to the term that decreases along reduction. Okay? There is actually an open problem, which was posed by Gödel for the simply type lambda calculus, so not for this calculus, so we didn't solve this open problem, which is about finding an easy way to an easy decreasing measure, which we are not going to dig into what easy means here. But well, so our proposal is a new decreasing measure, which we will discuss later how it compares with the existing ones. There are other two decreasing measures for this calculus. And the formal definition okay, first, our decreasing measure is based on enriching the system we have with memories. We will see later what this means. And the formal definition is it is a mapping from lambda term to some well-founded order, such that it satisfies the property that if I have a step from M to N, then the measure for M is bigger than the measure for M. And since the domain of the measure is a well-founded order, if I had an infinite chain of reductions firing from some program, then I would be able to reproduce an infinite decreasing change in the well-founded order, which doesn't make sense, right? So we have a proof of normalization for it. So in order to define this measure, we had to define an intrinsically typed version of idempotent intersection types. These systems are usually presented in the version a la Curry, which means extrinsically typed. And we were able to prove that the charge version we define is in simulation with the Curry system, with the usual system. I mean, this system simulates each other. We will see that graph in detail later. So first, this is the usual system. It was introduced in the 79, 80. There are two papers. So there are nothing new. Fortunately, I had Delia today introducing intersection types, so I don't have to dig a lot here. But the idea is that to the left of the arrow, I can assign a set of types instead of just one type. So I will say, okay, this parameter will have all these types, and then I have several occurrences of that variable inside the body of the function with one of those types. So we use these set notations since we are in the idempotent version of these systems. And we know that here, this is the rule, this is the more important rule of the system, which is where I assign a set of types to some term. And if I can assign all of these distinct types to some term, I will say it has this set term. Okay, and now we can start. I will start with the intrinsically typed version, the a la church version of the system. So why not to use the Curry version? Okay, from now on, when I say derivation, I will be meaning a term in the Curry system. And when I say term, I will be referring to a term in the church system. So the reason to use terms instead of just derivations is that our technique is based on radix degrees. This is actually a technique that was extended from the simply typed lambda calculus. And the way we handle the derivations, we need to make some changes in the derivations that produces intermediate steps that does not correspond to a derivation in the Curry system. So, for instance, we have that to give type to the identity here, which will give these two types, I need the same term in both of subderivations. But I want to be able to make changes, in particular to apply beta reduction to the green subderivation. So, and I also need to keep track of those changes in the term. So that's why you need the charge version. So the charge version transforms this rule into this other rule, where I have distinct types here because they are the charge version. So now I cannot assign different types to one term because the variables are annotated with their types. So there is only one type. We have type unicity here. And then instead of having only one term in the conclusion of this rule, I have a set of terms, which I will call a set term. This is a linearization, which is inspired by Kafuri's one. Now I will be able to do what you wanted, which is to make changes to the green part and keep track of those changes in the term. Okay, so now we have to pay attention to the substitution part. And in the system Alacurri, in the original system, the substitution is essentially the same as in the lambda calculus. We just take the argument and replace each occurrence of the variable by the argument. But now I want to, I have this term, this variable that has type A to A. So I have to assign the proper term to it, right? I have to maintain types. So, because I need to get this result, right? Because the term represents the derivation. So I need to do something like this, where I replace each term, S sub 1, for instance, by the variable x a sub 1, where a1 is the type of S1. And since we have a bisection between a set term and its corresponding set type, this is definable without problems. And we define it in a similar way to what is presented here. And this calculus satisfies the properties of subtract reduction from the injectivity and the type unicity and confluence. So we define the charge system. Now we're going to relate the derivation system and the type system. The Curry and the charge version. Well, there is a reduction difference, right? Because this, I have this set term, which is not a valid term in the derivation, but can be assigned a valid, we will see it later. But then I can apply reductions inside each term of the subterm. So I have all these intermediate derivations until I ended up applying the same step to all the subterms. Okay? So how am I going to relate the Curry system and the charge system? Well, I will show you with an example. If I have something like this, right? I have II and II. These are. Don't pay attention to the types. I just put them there to remember that there are types. Let's think this type. So I have the identity applied with the identity, and if I erase the types here, what they get is just the identity applied with the identity and the identity applied with the identity, and they are the same term. So when I have that in a set term, all the inner terms are the same term modulo erasure, then I will say that this term refines this other term. Okay? So this is the term that is corresponding, this is the derivation, sorry, in the Curry system that corresponds to this term in the charge system. these intermediate terms, where I have that the inner terms are distinct, modulo erasure does not correspond to nothing, are just intermediate steps for the charge calculus. And then when I arrive to some term that, again, all the inner terms of each set term is equal modulo erasure, I will say that it refines this other term. Okay, so with these notions, we are able to prove a correspondence theorem where M has its corresponding uniform term in the charge system, and if I erase the types, I get a derivation in the carry system. And then both systems simulate each other, which means that if I have a term n and a step to n, and t refines m, then I can get to an s that refines the m. And if I have a term t and one step to t prime, and I have that t refines m, then I can keep going from t prime, and I will arrive to some s that refines n when there is a step from n to n. So the system we defined behaves correctly. That's what we want to say here. So the part 2 now, the decreasing measure. So it is based, I already told you, on radix degrees. So what is a radix degree? It is the degree of the type of its abstraction. And what is the degree of a type? It is simply the height if we think of it as a tree. So for instance, in this radix, we will have that its degree is the type of the abstraction, which is A to B. And there is an observation by Turing, that same Turing, that says that a radix contraction can only create radixes of smaller degree. So if I think of this as a contraction of this radix, then I know that any new radix created there has a smaller degree than A to B. Okay? This is the core idea behind the proof of the decreasing measure. So we now define the memory calculus. What do I mean by a memory calculus? Well, we add a syntactic construction that is a memory, what we call a memory, where essentially what we want to do is to remember each consumed argument along reduction. So if there is a reduction step from this term to this term, then I want to remember the arguments. And I simply put it there. And it cannot interact with the rest of the term. And why not to erase? Because I want to retain not all the information, but I want to retain more information than what beta reduction usually does. So the information here in T is retained in all of its products. And this calculus satisfies the property we are most interested to show now that it satisfies is confluence, okay? So let's see an example of reduction here to make it a bit more clear. Let's say we have, I don't recall if it is the same example right now, if there was some little change, but I have lambda x applied to x, and then it is applied to the set term of II. Okay, yeah, I think it's the same term. So in gray, we have the radix that I am contracting, and in red, I have the memory that was created. Okay, so I create this memory here, I create this memory here, then I apply the head radix, and I create this big memory here, right, because it is all these arguments. And finally, I arrive to the normal form, where I have no more radixes, and I have a bunch of memories. Okay, so we define the calculus. Now we are going to define the measure, which is defined by operations over the calculus. The first operation is the weight of a term, which is the amount of memories it has. For the example before, it is 6. And next, the simplification of a term for some degree d. So the simplification, it is a function defined by a structural recursion, which essentially means the contraction of all the radixes of degree d. I put contraction there with quotes because it is not actually contraction, right? It's a function. We do not rely on reduction here. And since it is defined by structural recursion, which is what I try to highlight here with the gray colors, we know this terminates. Having defined this, we define the full simplification, which is the iterative application of the simplification, starting from the maximum degree and ending with the minimum degree. So with these operations, I'm going to define the measure. So let's say we have some term t. I told you we want to find something that shrinks related to the term. So we are going to get the full simplification of this term, which is going to be some term t prime with some list of memories. And then we are going to take the weight of that term, which is going to be simply the size of this list in some sense. So the formal definition is this one, okay? We take t, we apply the full simplification, and we weight it. So we define the measure, and we know it terminates because all of these functions terminate. So now I want to prove that it is actually a decreasing measure. So some properties about the simplification. First, reduction arrives at simplification. So t in some amount of reduction steps will get to the full simplification of t. Also, I know that that full simplification of t is actually a normal form for t. Since we have confluence, we know it is the normal form. And we know that if we take t, we apply the simplification of the maximum degree of t. And we say, okay, what's the degree of that simplification? It is going to be smaller than the maximum degree of t. So the simplification of the maximum degree decreases the maximum degree. And using these properties, we were able to prove the theorem that our measure decreases along reduction. So if we have one step from t to s in the church calculus, note that this is not in the memory calculus, this is in the church calculus, okay? Then we have that because all of this is defined in the memory calculus. So if we have the reduction step in the church calculus, then we know that the measure for t is bigger than the measure for s. So intuitively, what is happening here, I won't show the detailed proof, but I want you to grasp an intuition of why it works. Let's consider this step in blue, this reduction step in the church system, where I have x applied to II, and then again applied to II. I didn't put the types here to make it less confusing. And so in the church system, we see that II reduces to I, right? So it is clear that here we have one less relics, but it's not the important part. Or maybe it is. So note that I put the reduction, all the reduction tree for this term, but this is not the important part. This was just to show what's going on. The important part is the green part, which is that we compute this without relying on the reduction. Okay, we compute the normal form. And in the normal form of this term, we have two memories, right? One memory was created by the contraction of this redex here, and the other one by the contraction of this other redex. Okay? And if we go to reduct in the church calculus, we have that we only have one memory, right? And what happened is that here, this reduction step is not there anymore. So the memory that was added here by contracting that reduction step, I mean, the memory generated by this argument is here, but it's not here. And that's the idea behind why it works, okay? Okay, so to conclude, because this proof was for the church system, right? And we were interested in the carry system. But since given some derivation m in the carry system, we can simply decorate it and get its uniform term associated in the church system. We can do that, and we can obtain a decreasing measure for terms m, right? Because if I have one step in the carry system, I have at least one step in the church system, and the same measure still works. So as a corollary, as we said at the beginning, we have that the carry system is strongly normalizing. So the related works, the comparison I told you before. So there were other two there were two existing decreasing measures for idempotent intersection types. One was by Kafori and Wells, and the other was by Budul or Budol. Sorry again. So the domain of their measures is for Kafori and Wells, a multiset of natural numbers, and for Budol, a pair of natural numbers. And for us, it is a natural number. So in this sense, our measure is simpler, which is the main difference. And there is another important difference, which is the methodology, where their methodology is indirect in the sense that the measure only decreases for one specific strategy. They don't allow any radix to be constructed. They later rely on extending the proof of weak normalization that measures gives them to strong normalization. We have a direct measure where any radix constructed makes it decrease. And then the base calculus we use is a calculus a la Church, where we prove that it is in simulation with the correct one. And then for the future work, we would like to refine this measure to exactness, which means that the number we get is exactly the amount of maximum steps. I mean, the length of the longest reduction chain that you can fire from the program. This is done for the simple Italian calculus, and we are working in the. I mean, we are working in the version for intersection types, which resulted to be quite more difficult. We would like also to adapt this technique to the idempotent intersection type system, which characterizes head normalization. These systems we used here characterizes strong normalization. Okay, so thank you.